Hi, in this video we will learn about what is adaptive boosting. It's a type of machine learning algorithm, also known as Adaboost, by the way. Okay, so Adaboost is nothing but adaptive boosting. We'll first learn about what is boosting. So there are different types of boosting. So one of the type is adaptive boosting, but you also have gradient boosting and so on. We'll try to first understand what is boosting. The intuition behind boosting. It's a type of ensemble actually, with nothing but combination of many model, combination of decision tree models basically. Okay, we'll learn about the intuition behind it and how to build it, what are the packages available in R and Python, and how to assess the performance of such a model, how are they different from random forest, bagging boost, and logistic regression and so on. Okay, let's get started. Right, so before we understand what is adaptive boosting, it's important to understand first of all what is boosting. Right, as I've said, it's a type of ensemble modeling where you combine different models. Right, so how do you do that, and why is it even needed? Right, if you first of all, if you understand what is a decision tree, you know that decision tree is a very simple model, but it doesn't perform well, right? In many instances, it doesn't perform well. A decision tree model is very simple, right? It's looks something like this, very easy to understand, easy to build and understand, but doesn't perform well, right? Poor performance. So a decision tree model is a poor performing model. It's a weak model rather, right? So the idea of ensemble is that to take multiple data sets from one data set, and then fit a number of decision trees. It can be 100,000. It's up to you, right? Depending on how the more number of samples you take, the better is the model, and you combine the results, right? And I will understand as to how to combine the results from these hundreds or thousands of decision trees, and that gives that makes the model performance better actually when you combine results from various decision trees. So that's boosting. There are various ways of combining it. There are various ways of taking the samples actually. Taking such sample is known as a resampling, right? There are many ways to do that, but that's more or less what it is. And the way the various ways to do that, and depending on how you take the sample and how you fit the different models, you have different types of ensemble models, right? And boosting is one such ensemble model. You also have random forest and bagging to be other types of ensemble models. Okay, now decision tree, a single decision tree is a weak model, a weak classifier or weak regressor. It can it is good to understand it, easy to build, but it can also overfit the model, or sometimes even underfit. So the performance is poor, but an ensemble model does better job. So here is the way you do such a model. Right? You have such a sample, you have many data points here, right? So what you do is that you create many samples. Let's say you create 5 samples. You can make 50, 100,000, right? The more number of samples you take, the more accuracy you will have, right? Sample 1, sample 2, sample 3, sample 4, sample 5. Okay, and these observation in these samples have been taken from this particular population, but each observation can appear multiple times. That means it's sampling with replacement. Okay, so that's a very typical way of statistical sampling, which is sampling with replacement. Okay, and then you fit decision tree to each one of these sample. Okay, what is happening? You fit a decision tree to each one of these samples. So there will be 5 decision tree, right? Imagine it's a classification problem. You want to classify if someone has cancer or not, right? It's a healthcare data, and you have data for cancer patient, but also non-cancer patients. So there is a classification problem, right? Whether it's a yes cancer with the patient, a yes or no, right? Imagine the first decision tree give an answer of yes. So this is yes. Second said, oh, it's yes also. The third said no. Fourth yes. The fifth no. So there are 3 yes and 2 no, and hence when you combine, because you have more number of yes than no, the final result is yes. Okay. So if you combine results from more number of such decision trees, so it's likely to be more foolproof or more accurate compared to if it was just one decision tree, right? And this is for classification problem, right? It can also be for regression problem. Regression problem it's a continuous variable, right? So you just take the average of all of these results from all of these decision trees, right? Take the average of that, and we'll take some examples to understand it, right? Okay, to understand it better. So for classification, we take the maximum mode, like how we have taken here, right? More number of yes than no. So maximum mode, the one that is maximum, that is the final answer. Whereas in regression, it is just taking the average, right? Here is typical example. Imagine you have taken 7 samples, right? Normally in real, you take more than 100, right? The more samples you take, the better would be the model. Of course, it's computationally intensive, but nowadays it doesn't really matter actually, right? The first decision tree said the patient has cancer, second said non-cancer. Out of the 7 sample, cancer yes, there are 5 cases, cancer no 2, and hence yes is a clear winner, right? So that's how you aggregate the results, right? These are individual results from individual decision tree, and you aggregate that into. So that's a typical way of ensembling and boosting in particular, right? In regression problem, for example, you're trying to predict the salary of someone. It's a continuous variable, right? Salary is the target variable. It's continuous, right? So it's a regression problem. So in that case, you said simply take the average of the results coming from all the decision tree, right? First decision tree said it's 100k, 70k. You take the average of that. Here it's not the maximum vote, right? In classification problem, is the maximum vote, right? It comes out to be somewhere around 75k, right? So this is likely to be more accurate compared to the result from individual decision tree. Individual decision tree can be a bit more overfit actually. Again, the more number of samples you take, the better would be the model. There's no limitation to how many samples you can take. This is something you can choose yourself. When you build a model in Python or R, any of these statistical packages, you can always provide how many number of samples you want to take. You can take 100, 1,000, 10,000, even 100,000. If you take 100,000, it's going to run for a while. I think couple of seconds for sure, right? At least maybe more than a minute. It can be a bit time consuming, but it's worth doing that, because the more number of samples you take, the more accurate results or more stable result you will get, right? Otherwise, if you just fit a decision tree, it's easy to do that, but it's likely to be overfit. Okay, now adaptive boosting is a type of boosting. So we understood actually the theory behind the boosting. Boosting is one of the ensemble modeling technique. Actually, you also have random forest, right? Random forest, that's type of ensemble modeling. You also have bagging. Both are ensemble models, and uses the same principle, except the fact that the way you combine results, the way you use the variables, the features to build the decision tree model, that can differ, right? In random forest, you take only the best set of independent variables or features, right? So that's random forest. Banging is somewhat different in a way, the way you do the sampling. But boosting is of various types. You have adaptive boosting, you also have gradient boosting. You might have heard about XGBoost, right? Very popular algorithm. So it's a type of the boosting algorithm, right? When you build a model, you can also try both adaptive boosting as well as gradient boosting. This is a type of gradient boosting. You can also do adaptive boosting, right? There is no proof that one is better than the other. For one problem, adaptive boosting might outperform XGBoost. For some other problem, XGBoost might outperform adaptive boosting, right? So always good to try out more than one type of machine learning model, to get a higher accuracy. So what is adaptive boosting? The word means adaptive. That means you are adapting something, right, over time. So it's sequential in nature. So when you build this ensemble, right, here we have the samples. We created 5 independent samples. These are independent of each other, right? We created this 5 sample at once, fit them 5 different decision tree, collected the results and aggregated it. Whereas in adaptive boosting, we do it in sequence, right? And that hence the word adaptive. That means it is adapting over time, right? So there is a sequence to it, right? You have this main sample, you have data points, you created the first subsample, okay, randomly selected from the main sample. Okay, this is sample 1. If it's the decision tree, it turns out to be a misclassification, right? So what will happen is that the weighting next time in the second sample will happen in such a way that the probability of misclassification will be less, right? So we are sequentially changing the weight, okay, the weight using which the decision tree is built, right? So decision tree makes some adjustment in order to decrease the misclassification chances, right? And it goes on until the last sample, right? It can be 100, 200, 500,000 and so on and so forth, right? But it happens independently, sequentially, right, one after the other, and hence is called adaptive. Okay. All right, so that's adaptive boosting. It's the way you build a adaptive boosting model is very similar to how you build any other machine learning model. Understanding the intuition is very important actually. Of course, you are not going to write the entire module for yourself, right? You have packages nowadays in all kinds of platforms, whether it's R or Python or even SAS, MATLAB. So you just call the libraries and build the models. As long as you know how to build a model, how to test the performance of model, how to prepare the data set, I think you should be fine with developing a machine learning model, which is not a very difficult thing. But I think understand the intuition is very important, because you need to know at least how adaptive boosting is different from gradient boosting, and you must know actually what is boosting, and what's the reason why ensembling is done. If something really goes wrong, you want to dig into the details of it. Understanding the theory is very, very important, therefore, right? All right, so how is it compared to logistic regression, which is a very famous machine learning algorithm, right? Logistic regression is a regression algorithm used for classification purposes. And what you get out of logistic regression is probability of an event or probability of classification, right? You want to classify in something into 2 categories: probability of category 1, probability of category 2, and so on, right? And then using that probability, using some threshold, you divide that into 2 categories, right? Whereas in boosting, actually, you directly get category 1 or category 2. You don't get that through probability, right? And boosting can be, or adaptive boosting can be used both for regression, also for classification. So both for regression and both classification it can be used, right? It can be used, let's say for instance, you want to build a fraud model, right, in a banking setup, or you want to know default category, right? Whether there is any chance of default in a loan, you can use adaptive boosting there. You want to know whether a customer will purchase a product or not, you can use adaptive boosting, right? You can also use that in regression type problems where the target variable is continuous in nature. It can be like predicting, let's say, salary, predicting the number of customers that will purchase something in a given time. So for that kind of problem, you can use both problems, right? Whether it's classification or regression, you can use adaptive boosting. Okay. Right. So how it is compared with random forest, right? Another very popular ML algorithm. It's also an ensemble model, by the way. So it relies on this resampling, right? Taking multiple samples, fitting multiple decision tree, and then combining the results. Random forest exactly does that. But is the main difference between boosting and random forest is that in random forest you are a bit selective with respect to the features, variables that are used for model development, right? You take only the best set of features out of, if there are 10 available, you take the best set of maybe 4 or 5 for each individual decision tree, and it can vary actually. For one decision tree, maybe one set of 4 variables, the other maybe another set of 4 variables, right? But the steps are very similar. That's the only difference. And it's not sequential actually. Unlike adaptive boosting, this is random forest is not sequential. That's another difference. But in real world setting, you can try both random forest as well as adaptive boosting or gradient boosting. You can try all kinds of machine learning models and see actually which performs the best. And assessing the performance is perhaps by far the most important thing in machine learning. You need to do cross validation. You need to have training and test data set, building the model in train data set, and testing it in test data set, not just in one test data set but in multiple test data set, and that's where cross validation will be useful, right? You can find all this in scikit-learn, right? Whether it's random forest, logistic regression, all kinds of boosting algorithm, you can find in scikit-learn. Adaboosting is what to be used. Adaboost classifier if you want to classify, Adaboost regressor if you want to use that for regression purpose. In R, you have to use Adabag package. You have to install that. Okay, and how do you assess performance, right? Performance assessment itself is a very long topic in machine learning, right? You assess a performance in test data set, but it's also good to do cross validation. That means you test the performance in number of test data sets, and there are many ways to do it, using a k-fold or leave one out, cross validations, bootstrapping, bootstrap cross validation. So all that can be used. What is more important is to actually know what metrics to use. For classification, you can use various metrics such as AUC, accuracy rate, precision recall. For regression type problems, you use mean square error or mean absolute deviation, right? Even when you are using classification problem, make sure that you write metrics, right? Sometimes an F1 score or a precision would be a better measure of performance than accuracy rate. So pay attention to that, right? Depending on the problem, you will decide which metrics to use to assess the performance, right? All right, see you in another video.